Hi students, in the previous video we learned about the various kinds of charges and also properties of charges. So in this video we will understand Coulomb's law. So what is Coulomb's law and what is its formula? Okay. Now we learned that when two charges, stationary charges, are placed near each other, they either attract each other. That means if both the charges are of opposite nature, a positive charge and a negative charge, then they attract each other. And if they are both positive charge or both negative charge, they repel each other, right? So, but what is the force of this attraction or repulsion? That is what we need to learn, and that is obtained through Coulomb's law. So, Coulomb was a scientist and he did some experiments. So, what he showed was that, let's draw the picture. Now, this is one charge, let us say, okay, and there is a second charge, okay. Now they are shown as spherical, but this law applies to point charges. So we assume that if you consider, let us say, any spherical object, but if you see it from very far away distance, it will look like a point. So this is our assumption. There is a one point charge which is say A, another point charge which is say B, and they are separated by, so this is not a connection, this is not a connection, mind you, I'll just write it here. This two charges, point charges, are separated in space, let us say, by a distance r. R can be 1 meter, 1 kilometer, whatever, 1 centimeter, okay. So r, now they are uh, either attracting each other if they both are opposite nature charges, one is positive, one is negative. They are repelling each other if they are both same kind of charges, either both positive or both negative. So let us say charge on A1 is Q1, charge on A2 is Q2. Okay. So what is the force? We are only talking about the magnitude initially. So magnitude of the force is proportional to the product of the charges. This is what Q1 Q2 or Q1 into Q2. Okay. That is what Coulomb found. He also found that this force is proportional to 1 upon square of the distance. That means as the distance goes on increasing, the force technically goes on decreasing, and it doesn't decrease linearly. Let us say they are spaced 1 meter apart, there is a certain force. They are spaced 2 meters apart, the force is not half of the initial force, it is one fourth of the initial force. So it is decreasing as square of the distance. These two things he has found out. So combining these two, what he said was F is equal to K into Q1 into Q2 upon R square. Wherefore F is the magnitude of the force and Q1 and Q2 are the charges on the point charges A and B, and R is the distance between them, and K is a constant. So if suppose these two charges, point charges, are placed in free space, like not in air or something, free space, and if we are talking about the SI units, then K is equal to 1 by 4 pi epsilon 0, where epsilon 0 is called permittivity. So what is the uh, permittivity of charges by free space? If it is not a free space, epsilon 0 is permittivity. This is a constant. Okay. If it, instead of free space, these two charges are placed in any medium, air, water, liquids, and any other medium apart from free space, then this epsilon permittivity becomes permittivity of the medium, which is not epsilon 0, then epsilon. This will be in any other medium. This we will learn in the subsequent videos more about this epsilon. Okay, for now you understand it as these charges are point charges is first assumption, and second is they are placed in free space. So let us stick to this. So now in SI units, this value is 1 by 4 pi epsilon 0, and its value is 9 into 10 raised to 9. Okay, right? You will understand the units also. Now, what is the value of epsilon 0 permittivity of free space is 8.854, or we can technically say that also approximately as 9. into 10 raised to minus 12. This is the value. Units we will see. So if we want to know the units of K, for example, let's understand it like this. Force equal to K into Q1 Q2 upon R square. So if I only put K on the right side and shift everything on the left side, force into R square upon Q1 Q2. Unit of force is nothing but Newton. Unit of R is meter, so it will be Newton meter square, divided by unit of charge is Coulomb. So Coulomb into Coulomb, Coulomb square. This is the unit of K. So I will write it here. Newton meter square per Coulomb square is the unit of K. And similarly, we can find out epsilon 0 value and unit also. So 1 by 4 pi epsilon 0. So if I write here, let's now find out the unit of epsilon 0. Unit of epsilon 0. So we know that 1 by 4 pi epsilon 0, which we called K, is 9 into 10 raised to 9 Newton meter square per Coulomb. So if you only keep epsilon 0, so let us say epsilon 0 we have shifted to the right because it was in the denominator on the left side, it will go into the numerator on the right side, is equal to 1 by 4 pi into this figure, which is what we wrote it as 8.854 Newton raised to minus 12. So let us write it that way. So it is or approximately 9 into 10 raised to minus 12. Now what is the unit? When epsilon 0 goes here, this entire thing goes in the denominator. So here I will write Newton meter square per Coulomb. So when Newton meter square per Coulomb, so Coulomb is in the denominator of denominator, so it will be Coulomb, correct, upon Newton meter square. Okay, so this is the unit of epsilon 0. Okay, see K value Newton meter square per Coulomb square, so it is Coulomb square. Sorry, my mistake. Coulomb square. This is also Coulomb square because K, right? So let us correct that here. Newton meter square per square. This was already right in here also. So the unit of epsilon 0 is Newton meter square per Coulomb square in the inverse, that is Coulomb square per Newton meter square. And value of K is 9 into 10 raised to 9 and its units are Newton meter square per Coulomb square. What does this imply technically if you understand it like this? Now, if what is the definition of Coulomb? So if I write it as 1 Coulomb, so I will now define the force we mentioned as 9 into, or you can say in SI units, force between two point charges separated by a distance r in free space is 1 by 4 pi epsilon 0 q1 q2 upon r square. Let us say q1 equal to q2 equal to 1 Coulomb. So we can define 1 Coulomb and let the charges, point charges, be separated by a distance of 1 meter. So we have one charge which is 1 Coulomb, another that is plus 1 Coulomb, and this is also 1 Coulomb, and they are separated by a distance of 1 meter in free space. Okay, what does the force magnitude become? Force magnitude becomes force equal to this value, we know it is k1 by 4 pi epsilon 0, which is 9 into 10 raised to 9. q1 is 1, q2 is 1, so 1 into 1 will be 1, and this is r is also 1. So this many newtons. So now how can you define Coulomb? Coulomb is that charge which, if contained in two equal charges separated by 1 meter, they will experience a force of 9 into 10 raised to 9 Newton. Or we can say, if the force between two point charges separated by a distance of 1 meter in free space is this much, that is 9 into 10 raised to 9 Newton, then each of the point charges will have a magnitude of 1 Coulomb on it. Okay, 1 coulomb is a very big charge, because we know charge on an electron is 1.6 into 10 raised to minus 19 coulomb. What else we understand by this law is Coulomb's law is an inverse square law. Inverse square law because we discussed that it is proportional to 1 upon r square. Inverse square law. Just like gravitation force is also 1 by r square. It also has 1 by r square in the formula. Then Coulomb's law holds good for point charges only. So we are assuming that these are point charges. That is very important to understand. And mechanical force like friction, it operates when the objects are in contact, whereas Coulomb's force is a force which is not acting which is not acting for objects in contact. It is actually acting for when objects are separated also. So it can act at a distance also. Okay. This is called a field force. Any force which acts between two objects separated by certain distance is a field force. Gravitational force is also a field force. Electrostatic force is also a field force. Okay, this is what is the Coulomb's law and the force between 2 point charges separated by distance, and we understood it as a magnitude, right? Now, just to appreciate how much big this force is, this example you can read. So it's like, let's calculate the magnitude of force between two charges. Each charge is 1 coulomb and they are separated by 1 meter. So we found that it is 9 into 10 raised to 9 Newton, right? Which is a very big force, right? Which is a very big force. So what is the force equal to is, that force is equal to approximately 10,000 loaded buses and total weight of the buses, and it's still larger than that. You understand by that? Okay, just to appreciate. This is about in case the point charges are placed in a medium which is other than vacuum, then we talk about epsilon, which is permittivity in that medium. And then the ratio of forces is ratio of the permittivity constants. And then we talk about that ratio as epsilon r, relative permittivity. It is also called as dielectric constant. For now, just remember this, that epsilon r is nothing but relative permittivity when we are talking of two different media. One is medium other than free space and the other is free space, and this epsilon r is also called as dielectric constant. Okay, we'll understand this in next chapter at electric potential. For now, just remember this formula. Now, one more thing we need to understand is vector form of Coulomb's law, because force is a vector. So now let us draw a diagram containing that. So this circle, just understand it as a point charge. Let us say we have 2 point charges and both are having plus q charges for simplicity, or plus q1 and plus q2. Okay, this is point A and point B, and they are separated by a distance r. Now we understood the magnitude of the forces, but we need to now understand direction of the force, because these two are like charges. Obviously they will repel each other, so the force will be in this direction on the object A or the charge A due to charge B. Similarly, the force on charge B due to charge A is on this in this direction. We write it as F on A due to B. We write this as F on B due to A, just to identify them. We need to understand that this force acts along the line joining the charges. It's not acting, let us say, here or somewhere else, along the line. Now, because these two are like charges, therefore the forces are in this direction, opposite direction, and leading them away from each other. Suppose we have two charges at the same points A and B, but instead of plus Q1 and plus Q2, let us say this is plus Q1 and this is minus Q2, or let us say plus Q2 and minus Q1, whatever, and they are separated by the same distance r. So magnitude of the force will not change, but now the direction will be towards each other because it's an attractive force, but it will be along the line joining the two charges only. This will be now the F on A due to B, and this will be F on B due to A. And whenever we are representing vectors, we represent them through arrow marks, right? Here also. So this is the vector form. So how do we write it then? Formula F on A due to B vector is nothing but K, or 1 by 4 pi epsilon 0. Let's write 1 by 4 pi epsilon 0 to make it simpler. 1 by 4 pi epsilon 0 q1 q2 upon r square, correct? But r is now the displacement vector, so it has a magnitude and a direction. So we can write this is r, and r is within 1 and 2, or r a and b, let us say, and this is a vector and square of this vector. We can write it as, because any vector can be written as any vector, let us say RAB is a vector, it can be written as magnitude of the vector, which can be written like this, multiplied by unit vector, which is written like this. So in this notation, if we write the force, so force on A due to B is equal to 1 by 4 pi epsilon 0 q1 q2 upon RAB vector, its magnitude and square of that magnitude, multiplied by, because it is in the, it's not actually multiplied by it, we can say it is R unit vector A and B along that direction, right? Or we will not write RAB here because this is RAB in the denominator, okay, unit vector, and actually that is, when we come into the numerator, it will be RBA, okay? So why RBA? Because RAB is in the denominator, and when we take it to the numerator, it will be RBA. Now the RBA is a, this is a unit vector, sorry. So RBA is a unit vector pointing from B to A. This is RBA. And of course, the force on A to B is in that direction only, along the unit vector RBA. That's why it's like this, okay? Understood? So I will write it in two steps for clarity. This is RAB square, which is a vector. So vector is equal to magnitude into unit vector, and it is unit vector RAB in the denominator. So when it is taken to the numerator, it will be FAB equal to 1 by 4 pi epsilon 0 q1 q2 upon magnitude of a distance and square of that, multiplied by, when we take it to the numerator, it will be RBA, which is the unit vector from B to A. So this is the same direction. Unit vector always tells the direction. So this is the vector analogy. If you are not comfortable with this, stick with the formula for now, but just remember this. And once you understand vector algebra, you will be better able to appreciate this vector analogy of the force. Okay. And obviously these two directions are opposite. So if you take one direction as positive, the other direction will be negative. That is what I said. F on 1 due to 2 or A due to B is minus of F on B due to A. Magnitude is same, directions are opposite. Okay. So in general, we can write the formula like this. That is what we have written here. Okay. Now let's understand principle of superposition. So let us say we are now talking of, till now we have talked of only 2-point charges separated by distance. Let us say we have 3-point charges. So, or more than 3-point charges. Let us say we will build the picture. First, initially this is Q1 at A, and this was at B Q2, and both are point charges. So we said force on A due to B, or force on B due to A, is nothing but 1 by 4 pi epsilon 0 q1 q2 upon, if they are separated by distance r, let us say, to distinguish from other charges, we will say r12, it's a vector. So r12, its magnitude square, and multiplied by r21 unit vector. This is what is the force. Now imagine that we have another point charge C. Now force on A due to C, force on A due to B, and force on B due to C, and then we will have to understand the overall force. Let us say we are talking about charge A. So charge A will experience a force due to charge B, and charge A will also experience a force due to charge C, and the vector addition of these two forces will be the net force on the charge A. That is what is the principle of superposition. So what is it saying is that net force on charge A is equal to, if I only consider charge A and charge B, so it was net force on charge A due to charge B. If I only consider charge A and charge C, then it will be force on A due to C and the vector addition of these two forces. So if there are more number of charges in the vicinity, it will simply be the vector addition of the forces on a charge due to each of the other charge, as if other charges are not existing. That means if there are three charges, don't consider three charges, just consider two charges A and B and see what is the force on charge A due to charge B, that is this. Then consider other scenario where charge A and charge C are only present. What is the force on charge A due to charge C alone, that is this. Add these two vectorially. This will be the net force on charge A in the presence of two charges. Similarly, if there is one more charge D, then it will be force on A due to D also vectorially added. Now, how do we add this? That's what we will learn, and then we will go to the next concept. Okay. The more you will understand the vector algebra, the easier it will be to understand these things. Okay. So let us say this is A, this is B, and this is C. Here the charge is Q1, here it is Q2, and here it is Q3. Let us say this distance is R or R1, I will say, or RAB, whatever you want to call it. Okay. So let us say it is RAB. This distance is RAC. They are actually displacement, but let's talk about the magnitude. So RAC. This distance is RBC. Now, if I want to calculate the force on charge A, it is equal to force on A due to B plus force on A due to C and their vectorial addition. What is force on A due to B? For a second, forget charge C. So force on A due to B is 1 upon 4 pi epsilon 0 Q1 Q2 upon RAB, this vector's magnitude, and square it, and then RBA unit vector. Similarly, this is force AB. Similarly, force AC, just focus on A and C. It will be 1 by 4 pi epsilon 0 Q1 and charge C at C is Q3, Q1 Q3 upon RAC, its magnitude, square of that, multiplied by RCA unit vector. This is RCA unit vector. Because all three are positive, we consider that as RCA unit vector. Okay. Okay. Consider all these are positive charges or all these are negative, like charges we are talking about for simplicity. So this is the overall force on charge. Now how do I draw it is vectorially. What is the direction? Let us see. If I only consider A and B, we understood previously that this was the force. So this is force on A due to B. If I understand only A and C, this will be the force along the line joining A and C but opposite to C. Okay. This is force on A due to C. These two vectors. So let us develop these two vectors. This is our force on A due to B. This is our force on A due to C. I am just keeping the line lengths different to explain better. So as per the parallelogram law or triangle law, anything you can calculate. So let us set parallelogram law. You make it a parallelogram by joining the end of one and extending parallelly and intersecting with the other line starting from the other vector end. So to create a parallelogram, and the diagonal of the parallelogram is the addition, vector addition result. So this is the force on A. In this case, this force on A will be somewhere here. This is the net force on A. Okay. So that is what superposition principle says, that when there are more than two charges in the vicinity of each other, force on a particular charge due to all the other charges is nothing but vectorial addition of forces on that considered charge due to each of the other charges. So F12, F13, F14, as if when you are calculating the forces on a charge due to other charge, that is each of the other charge, you are ignoring the presence of remaining charges. So let us say, let's read the part of the text. If there are more than two charges, okay, calculate the force between any two charges using the Coulomb's law, and then force exerted on a particular charge, let us say Q1, due to all other charges is nothing but vector addition. This is known as principle of superposition. So with this, we can understand this question. Okay, let's see what this question is. A charge plus Q is placed equal to 12 Coulomb is placed at a distance of 4 meter from another charge plus Q is equal to Q2 is equal to plus 6 Coulomb. The figure is like this. Where should a negative charge be placed on the line joining these two charges so that this charge does not experience any force? So that means, let us say this was our first charge and this was our second charge. Okay, this was having Q1 charge, this was having Q2 charge, and let us say this is the line joining the two charges. So he's asking, at what place should a third charge be placed? Let us say a third charge is placed at this point C. And what is the third charge? It has charge Q3. So this charge will experience a force due to charge A. It will also experience a force due to charge B. So first is, what is it saying? This is a negative charge. So Q3 is negative. Let us say it is minus Q3. This is plus Q1 and this is plus Q2, just to distinguish it. Okay. So now this charge will get attracted towards B. This charge will get attracted towards A. It should have no net force. That means force on C due to A, attractive force, and force on C due to B, that net attractive force. They should be balancing each other because this attractive force will be in this direction. This attractive force will be in this direction. This is F on C due to A. This is F on C due to B. Both should be equal in magnitude and opposite in direction. Only then this charge will not experience any net force. That is the logic. Now, what are the data given in this question is, these two charges are separated by a distance. How much it is mentioned? 4 meter. Okay, and charges, this Q1 is having 12 Coulomb plus 12 Coulomb, and charge 2 is plus 6 Coulomb. Okay, and charge 3, Q3 is not mentioned. It's not mentioned if you see. So let's find the formula. Force on 3 charge 3, or let us say here we have mentioned C. So let's force on C due to A. Formula is 1 by 4 pi epsilon 0. Q1 is 12 into Q3. Because it is Q3 is negative, so this will be, I will write it minus here. Upon what is the distance? Let us say this distance is x. So x square. We are talking about only the magnitude because that should be equal. Now force on C due to B magnitude is nothing but again minus 1 by 4 pi epsilon 0 plus 6 Q3 upon, already minus I put it here. What is this is x, so what will this distance be? Overall distance is 4, so 4 minus x. This is 4 total, this is x, so this is 4 minus x, so 4 minus x whole square. We know the direction will be exactly opposite because it is along the line joining the forces. This will be this line, this will be this line. They are equal in magnitude and opposite. So these two are equal. So we are equating 1 and 2. What is this? That means we are saying force on C due to A in magnitude is equal to force on C due to B. That is why the net force is 0 because they are acting in opposite direction. So just join the right hand side, just equate the right hand sides. We will have 1 as 1 pi 4 pi epsilon 0 12 Q3 upon x square is equal to minus 1 by 4 pi epsilon 0 6 Q3 upon 4 minus x whole square. And here these two will get cancelled. Okay, so what will remain is 12 Q3 upon x square is equal to 6 Q3 upon 4 minus x whole square. Now Q3 also gets cancelled. That's why Q3 value is not required here. And 6 and 12 get cancelled. This will become 2. So it will be 2 upon x square is equal to 1 upon 4 minus x whole square. On solving, you will get 2 into 4 minus x whole square equal to x square. And this will be, if you open the bracket and develop it, it will be a minus b, a square, a minus b whole square, a square plus b square minus 2ab. So this will be, if I open the bracket, 32 plus 2x square minus 16x equal to x square. This will be 2x square, and this x square, when it goes to the left, it will be minus x square. 2x square minus x square. So it will be 32 plus 2x square minus 16x minus x square equal to 0. And simplifying, 2x square minus x square is x square minus 16x plus 32 is 0. On solving this quadratic equation, what do we get? So what is the solution of a quadratic equation? Formula is, if it has two roots, so alpha is equal to minus b plus under root b square minus 4ac upon 2a. This is one root, and beta is minus b minus under root b square minus 4ac upon 2a, where the equation, quadratic equation, is ax square plus bx plus c is equal to 0. If this is the quadratic equation, then this is the two solutions. Now here a is equal to 1 in our case. You compare this equation with the standard equation. B equal to minus 16, C equal to 32. So just put the values here now. One of the roots is minus b. Minus of minus 16 is 16. Plus or minus b square is 256. Minus 4 into a is 1. Into c 32. 4 into 32 is 128. Divided by 2 times a. 2 into 1 is 2. Is equal to, and I have written alpha and beta. So alpha is minus 16 plus. So let's first calculate alpha. So 256 minus 128 is 128, square root of 128. Okay. So 16 plus, what is square root of 128? 16 sevens are 112, 16 eights are 128, right? So this will be 128 divided by 2, which is, again, I will solve it. This is nothing but under root of 16 into 8 by 2. Okay. And this is nothing but under root of 16 plus, this is, sorry, not plus, into 16 is nothing but 4 into 4, and 8 is nothing but 4 into 2 upon 2. So it is nothing but 16 plus this 4 into 4. If you bring outside the square root, it will be 4. This 4 is 2 into 2. So this is 4 into 2 and under root 2 upon 2. So 16 plus 8 root 2 upon 2, it is nothing but 8 plus 4 root 2. This is one of the thing. Okay. And beta is nothing but the other thing. So these are the two values of x. So let us check it with here. So it's approximately 2.35 meters and 13. So this will be 13.8 plus 4 is 12. And so this will be 13.65 approximately if you use the calculator. 13.65 meter. And the other value beta is similarly, beta is the same thing but with a negative symbol here. Okay. So 16 minus under root of 256 minus 128 upon 2. See, other things are same. So it will be, if you see here, if you see here, Finally, it will be 8 minus 4 root 2. Okay. Let's see what's happening here. So it will be 8 minus 2 root 2. And 8 minus 2 root 2 is nothing but, if you see here, it was what? This was 8 plus 4, sorry, 8 minus 4 root 2 it will be. This new page is not appearing. Let me check whether it's the next page. Okay, next page is here. So 8 minus 4 root 2, not 2 root 2. And this will be, as mentioned here, it is approximately 2.35 meter. That means if this is A and this is B and this is C, so this C is at a distance of X, which is either it is 2.35 meter away from A. So this is 2.35 meter. So what this should be? This should be 4 minus 2.35 meter away from B. Or in the second situation, it is this is A, this is B, and C is on this line only, but it is away from A and B. Let us say this is C. And this C is X meters away from A. This X is 13.65 meter. Okay, and this will be 13.65 minus 4 is 9.65 meter. So it can be away from them. It need not be between them. It can be between them when it is at 2.35 meter away from A, or it can be on the extended line of A and B and away from both of them. So total 13.65 meter from A. In both these situations, this charge at C will not experience any force due to charges A and B. That is the solution. Next, we will see one more question. So two charges, each of 6 into 10 raised to minus 10 coulombs. So though they are like charges with same magnitude. They are separated by a distance of 2 meter. Calculate the magnitude of Coulomb force between them. Very simple. So it's just apply the force formula. K value is 9 into 10 raised to 9. And each of the charge is 6. So 6 into 6 into 10 raised to minus 10 into 10 raised to minus 10. They are separated by a distance 2 meters. So just apply. This will be the magnitude of the force. And it is a repulsive force. Very easy, right? Now I want you to solve these questions. So same thing, two charges are mentioned, their magnitude are mentioned, they are separated. This symbol micro means 10 raised to minus 6. Huh? So first charge is 16 into 10 raised to minus 6 coulomb, second is 9 into 10 raised to minus 6 coulomb, and both are like charges, positive charges. They are separated by distance 12 meter. So magnitude of the force experienced by Q1 due to Q2, and what is its direction? Okay, right? And what is the direction of the force experienced by Q2 due to Q1? This you can solve and let me know. And then also we will discuss the solution in a separate video. And then second is there are 3-point charges as mentioned in the figure, and the charges at C and B are positive and same magnitude. Charge at A is negative but magnitude is same, and it is in a right angle triangle. Okay, it's mentioned three corners of a right triangle. Now in this right triangle AB equal to AC, so that means it is an isosceles right triangle. So what is the magnitude and direction of force on minus Q? Let's solve this. Okay, I want you to try it out on your own first, and if you don't get it or after you solve it, you can refer to the solution. So this is an isosceles triangle, these two sides are equal. This is B, this is A, this is C. Here there is a charge plus Q, here there is a charge plus Q, here there is a charge minus Q. Now we want force on minus Q. So force on A due to C plus force on A due to B. The vector sum of this is nothing but net force on A, right? Now what is the force on A due to C? Its direction will be its attractive force, right? Because force on at A, the charge at A is negative and charge at C is positive, so this will be attractive and acting along the line. This is force on A due to C's direction. Okay. So what is its magnitude? Its magnitude is 1 upon 4 pi epsilon 0 or 9 into 10 raised to 9, because assuming they are in free space and nothing is mentioned, so we assume, and into q1 q2. So minus q into q is minus q square, because minus of q into q, minus q square, or in order to avoid confusion I will put the minus sign here. This is q square divided by, what is the separation? AB and AC are equal in size, so let us say if this is R, this will also be R, so let us say it is R square. Now force on A due to B, this will be again attractive force and it will be towards this. Okay, so it is nothing but 9, and we are calculating magnitude, so let's calculate to 10 raised to 9 into q square, again minus sign is there, upon R square. So magnitude wise same, but they are acting at right angle to each other, and because the charges magnitude are same and the R is same, that is in both cases the vectors will be of equal magnitude. So the net force on A will be in this direction. Okay, right? So what is the magnitude net force? Magnitude is nothing but, we have to see this force. Okay, this force is acting exactly perpendicular to it. Okay, so there is a formula for vector addition magnitude. Okay, and the direction we can still point out here. Okay, we will calculate the magnitude. Okay, in this case we can say these two forces are acting 90 degree to each other, so we can use the triangle law and shift this force, because considering these forces are free vectors, shift this force to start at the end of tip A, and this will be the resultant force. So it is nothing but this is the net force on A, right? So it is nothing but the hypotenuse. So magnitude of this square plus magnitude of this square, and then we square root the sum. So square of this, add them and square root. So magnitude of net force on A is nothing but square of this. Okay, it will, that negative sign will go off, square of this negative sign will go off, so it will be 2 into 9 into 10 raised to 9 into q square upon r square, and square root of this. Okay, and this 2 into 9 into 10 raised to 9 whole square it will be. Okay, and we are charging initially, and here it will be q square cos square, so q raised to 4, r square cos square, r raised to 4, so it will be nothing but 9 into 10 raised to 9 into q square upon r square into root 2. This is the magnitude. And what is the direction? This is nothing but tan theta. If this angle is theta, this net force is at an angle of theta with the horizontal, and tan theta is this upon this. So nothing but both are equal in magnitude. So tan theta will be nothing but 1, or theta is 45 degrees. This is a simplified case. We have a generic formula also for magnitude of the resultant vector and direction of the resultant vector. That's not necessary here. This is a simplified case because both are acting perpendicular. So it's easier to calculate the net force, which is nothing but this magnitude is equal to the length of the hypotenuse of this right triangle. And because these two are equal, this is an isosceles triangle, so force and charges are equal, so definitely the force magnitudes are equal. So therefore when we divide the vertical line divided by horizontal line of right angle triangle, it will be 1. they're equal. So tan theta is 1, theta is 45 degrees. That is the net force. So net force we will draw here using this font. Net force on A is exactly like this 45-degree angle it will make with respect to the horizontal, and its magnitude is calculated by this formula. Okay, 9 into 10 raised to 9 into q square upon r square multiplied by root 2. If we know q square and r, q and r value, we can calculate the value. Hope this is clear. In the next video, we will understand what is electric field and its properties.